So the goal of this discussion is to talk about the special reactivity that occurs at the benzylic position of aromatic rings, where I've listed here at the top what we're referring to when we talk about the benzilic position. We go back to our discussion of nomenclature. Hopefully this rings a bell to you. So the benzilic position is referring to the first carbon from the aromatic ring. So whatever that first carbon atom is, it doesn't matter how long the chain is after that, we're always referring to just that first carbon atom, because that's where we're going to see special reactivity take place. And so that's one of the reasons why we have a special way of referring to this particular carbon atom and the hydrogen atoms that are bonded to it. So what we're going to talk about first is why it is the case that we will see special reactivity at this benzylic position. Why is this benzylic position, in many cases, particularly capable of undergoing chemical reactions? And the reason that we'll see the benzylic position is particularly capable of undergoing some different types of chemical reactions, such as nucleophilic substitutions, if there's a leaving group bonded there, is because the radical intermediates, particularly carbocations and carbon radicals, are going to be particularly stabilized by resonance. So let's take a look at the reaction intermediates, specifically carbocations or carbon radicals, that would be involved in reactions at this benzylic position. So taking a look at the stability of carbocations that are benzylic, or carbon radicals, which I'll just indicate a C dot here because remember a carbon radical has an unbonded electron. So we'll look at the stability of carbon radicals or carbocations at the benzylic position. This is relevant because carbon radicals and carbocations are pretty common reaction intermediates. And so if we can create a situation where we have a very stable carbocation or carbon radical, that's going to yield reactions that are quite favorable as well, because that means that that reaction is going to have a lower energy intermediate. Lower energy intermediates are going to be able to form faster than higher energy, less favorable intermediates. So for example, if we were taking a look at and comparing the energy of some different types of carbocations as an example, and we could also do the same type of comparison here for carbon radicals and reach the same conclusion. So let's say we have a carbocation right here at the benzylic position. That would be a tertiary carbocation at the benzylic position because we have 3 carbons directly bonded to our carbocation. And let's say we want to compare that to a typical alkyl carbocation that is also tertiary. So if we were trying to compare the stability of these two, we could ask ourselves the question of which is more stable. Because the one that is more stable is going to be able to form faster during chemical reactions because of the fact that it's lower in energy. And this is going to enable us to create product faster. So it's going to create basically a molecule that is more reactive if we're able to make an intermediate that is relatively stable. That means that the energy barrier to go from reactant to product is going to be less dramatic. So we could think of it as an energy diagram, like so. So if we wanted to make a reaction coordinate, basically, we're trying to plot going from reactant to product in terms of the energetics of the system. We'll just look at a simple one-step reaction mechanism here with a carbocation intermediate. So we have our energy plotted on the y-axis, reaction coordinate or reaction progress on the x-axis, and we're going to start with the reactant. Then to get to the intermediate, we need some energy. The intermediate is generally going to be less stable than the reactant or the product. And then we come down here to the product. We'll say that the product is lower in energy than the reactant. So a couple of possible scenarios are like so in green, or alternatively in blue. And what we would see here in the middle, at that high energy point, is our carbocation intermediate. And the structure of that carbocation intermediate is going to determine how steep and how high this required energy gets. Noticing that the trend, or the line in plot there in blue, has a lower required energy of the intermediate than the one shown in green. And so what we're implying here is that the carbocation intermediate in blue is more stable, lower in energy, than the one in green. So the carbocation in blue there is more stable, lower in energy than the carbocation in green. That means it's going to form faster and it's going to yield product faster. So we describe that reactant as being more reactive. So we need to think about which is going to give us greater stability of the carbocation intermediate, starting with benzylic carbon or a standard alkyl carbon that forms a carbocation. So we're going to be comparing these two scenarios up here to ask ourselves which of those is more stable as a reaction intermediate here. So when we're traveling along the reaction coordinate here, which one is going to have a more favorable energy to therefore yield a product more quickly. So if we take a look at a tertiary carbocation, we need to think about factors favoring stability of carbocations. So what's going to stabilize those reaction intermediates and make them form faster? So this would apply both to carbocations and also to carbon radicals. We think of carbon radicals in terms of stability as behaving rather analogously to carbocations. So factors that give stability to carbocations basically are going to rely on electron delocalization. So we're trying to move around electrons to delocalize or spread out that positive formal charge. So we want to, in order to give stability to the carbocation, what it's going to come down to is stability is increased by electron delocalization. So we don't want that formal charge basically to be locked on just the carbon atom. We want to be able to share it with other atoms. And there's a couple of main ways that we can go about delocalizing electrons or sharing electrons, spreading out those over multiple atoms. Those two ways, the two main ways of electron delocalization, are that electrons can be delocalized via induction, which we could really think of as the polarization of bonds, where, for example, alkyl groups are electron donating. So if we have alkyl groups surrounding the carbocation, they're going to tend to donate electron density toward the carbocation and therefore make that carbocation less intensely positively charged. So alkyl groups are electron donating, and by donating that electron density, that's going to help stabilize the carbocation. That's why a tertiary carbocation has 3 alkyl groups bonded to it is more stable than a secondary carbocation that has only 2 alkyl groups bonded to it. Because of the fact that the more alkyl groups we have there to donate electrons, the more stable that carbocation is going to be. So that's one route to give stability to a carbocation. The second route, and the stronger factor generally, if possible, is going to be resonance. So resonance, remember, is where we can actually draw multiple valid Lewis structures by pushing electrons around within the molecule. So when we're thinking about what's going to give stability to a carbocation, these are the two things that we need to keep in mind. That we want to delocalize electrons by induction and or by resonance, where resonance is going to be a stronger force in determining the stability of that carbocation. A more stable carbocation is going to be able to form faster and thereby lead to a faster overall reaction. So if we take a look at our 2 examples of carbocations, we had a tertiary alkyl carbocation in comparison to a carbocation at the benzylic position. That is only the first carbon removed from the aromatic ring. So we also did a tertiary carbon there, so that we're comparing apples to apples here as best as possible. The only variable here is aromatic ring adjacent versus no aromatic ring, just a standard alkyl group. So if we take a look at the tertiary carbocation on the left, and we ask ourselves what factors are going to stabilize that, the only thing we can come up with here off the list of factors that can stabilize carbocations is it's going to be stabilized by electron donation from those three alkyl groups. So it's got the three alkyl groups bonded here, here, and here. And those three alkyl groups are going to stabilize that carbocation by induction. So it's going to be stabilized by induction from three electron donating alkyl groups. And since there's no pi electrons or lone pairs here, there can be no resonance. In order for there to be resonance, there always have to be pi electrons and or lone pairs. So when doing this analysis of stability, there is no opportunity for resonance here. So what about if we take a look at our aromatic ring over here and that carbocation that's at the benzylic position? So I'm going to draw out the actual Lewis structure of this rather than our abbreviation of having a circle inside the aromatic ring. So we're going to put in our three alternating single and double bonds in there. And we'll ask ourselves again about factors that will stabilize here. And we're again keeping in mind that resonance is a stronger force for stabilizing molecules than induction. So if we take a look at the structure of this, we would see that we could have some opportunities for induction here because we have our two CH3 groups here, for example. So there is some stabilization by induction here from the two alkyl groups, the two methyl groups. So I'm going to go ahead and add that to the list, but I think there's going to end up being something else more important going on here. So this is stabilized by induction from electron donation by the two methyl groups that we have bonded there. Then we need to take a look at resonance here. And resonance is going to be the game changer. So when we take a look at the resonance that's going on here, we have our aromatic ring adjacent to a carbocation. So we're going to have some extra resonance structures that we can draw here by moving around those pi electrons from the aromatic ring. So let's take a look at the resonance that's possible here for this structure. So what we're going to see is that the resonance is going to delocalize that positive formal charge. It's going to share that positive formal charge across multiple carbon atoms. So the positive formal charge isn't going to be locked just on that carbon atom. And instead, we're actually going to be able to see that through drawing multiple Lewis structures for this, we can move that positive formal charge around and share it across several different carbon atoms of the aromatic ring. So resonance is definitely going to delocalize that positive formal charge over multiple carbon atoms. So let's take a look at those other possible resonance structures here. So our resonance arrow, we will go ahead and draw some electron pushing going on to illustrate what's happening here. So we're going to take the pi electrons from that carbon-carbon double bond. Those are going to tend to be drawn toward the positively formal charged carbon atom. So if we can move pi electrons toward that positive formal charge without going over the octet rule anywhere, that's going to be a very favorable thing to happen, and we can definitely do that here. So just following that one arrow that we've shown here, we can go ahead and make a second resonance structure that will have moved that positive formal charge onto a different atom. And that's going to be a very favorable thing in terms of increasing the stability of this molecule, because that's going to delocalize, it's going to move around that positive formal charge. So after we do that electron pushing step, once we've moved the pi electrons from the ring up to here in that black pi bond that I just drew in, we're going to see the positive formal charge is now down here within the ring. And we can continue going with that. So with this theme, we can go ahead and draw some additional resonance structures to further delocalize that positive formal charge. And by further delocalizing that positive formal charge, we're further stabilizing the molecule here. Remember that the actual hybrid structure of this we could think of as a weighted average of all of these different possible resonance structures. And so we're going to have several different possible resonance structures here that are effectively going to result in that positive formal charge being shared across multiple carbon atoms. So we're drawing in our third possible resonance structure here. So far, so good. Now our pi bond that we just moved. I'll show the one that we just moved here in black. It's going to be right there. Our positive formal charge will have relocated to here. And we can go ahead and see if we can draw out even another resonance structure here. And we can do that by taking and continuing this theme of moving pi electrons around. You'll notice in each case they're moving toward that positive formal charge in order to move the positive formal charge around. That's creating resonance that's basically productive, meaning it's going to be generating a more stable molecule for us. So now that we've moved our pi electrons there from the red bond over, that will put those right here in black, and our positive formal charge will go here. And then I think at this point the additional resonance structures that we could draw would end up repeating resonance structures that we have already seen. So we don't want to draw the same resonance structure twice, but we basically worked out these resonance structures, so we've delocalized the electrons at each spot possible around the ring to give these 4 total structures. So this is quite a broad example of resonance because we're sharing the positive formal charge not just across 2 carbon atoms, we're sharing it across 4 carbon atoms here. And so that is going to lead to a lot of extra stability for the carbocation intermediate at the benzylic position relative to having a standard carbocation like we've thought about before, where it's just a typical alkyl group with a carbocation on it. So this resonance effect here is going to lead to definitely increased stability of the carbocation intermediate at this benzylic position relative to other carbocations, and that's going to allow reactions at the benzylic position to take place relatively readily. And what we're going to see here is that we could also go through a similar exercise if we were working with a carbon radical at the benzylic position. So what we're going to see is the total effect here is that both radicals and carbocations are really favorable at the benzylic position. And so we're going to see reactions that involve carbon radicals and carbocations taking place very typically at the benzylic position. So we're going to look at some examples of those types of reactions for aromatic rings that have a benzylic carbon. So first off, what we're going to look at for specific reactions at the benzylic position is we can do a throwback here to our SN1 reactions. So our nucleophilic substitution reactions at the benzylic position. So our SN1 reactions at the benzylic position are going to be very effective with secondary or tertiary carbons. Secondary, tertiary benzylic carbons. That are bonded to a leaving group. And we'll abbreviate the leaving group as LV. Remember that common leaving groups are things like halogen atoms. So we'll abbreviate halogen as X. So we're looking at benzylic carbons here that are bonded to something that can easily break away because the bond to the carbon is relatively weak and because that leaving group is itself a relatively stable product. So if we break away a chlorine atom, for instance, the product is going to be Cl-. That's a relatively stable anion, and so that's going to give a reaction that's relatively favorable here. So let's take a look at, and we'll do the mechanism for an aromatic ring bonded to our leaving group, our chlorine in this case. And we're going to react with methanol, CH3OH, and we're going to ask ourselves what the product is and what the mechanism for this reaction is. So taking a look at the reaction mechanism for an SN1 reaction, keeping in mind that we can form a very stable carbocation here. An SN1 reaction mechanism, if you think back to chapter 9, the first step of the mechanism is that the leaving group leaves to give a relatively stable carbocation. And that can definitely happen here because we have that stabilization by resonance. Typically we think of secondary carbocations as not being as reactive as tertiary carbocations in nucleophilic substitution with SN1, but here certainly we're expecting an SN1 mechanism because we can make a really stable intermediate here. So first step of the mechanism, the leaving group leaves. To generate a carbocation, and not just any carbocation, but this is going to be a benzilic carbocation. So we can go ahead and show that taking place. Run my lone pairs. Leaving group breaks away. And that's going to give us our intermediate here. So our carbocation intermediate. Like so. And remember that the crux of why this is stable is due to resonance. So we're going to go ahead and write out the resonance structures for this. And based on the information that we learned above, you should be able to write this out now pretty much on your own. So go ahead and give that a shot. So we'll go ahead and try to write out the resonance structures for this. So I'm going to go through the solution here. So that was our first resonance structure that I've just drawn in blue. And then to stabilize that positive formal charge, we want to share it across multiple atoms. We can move those pi electrons over one spot there to delocalize that positive formal charge. We're going to share it across multiple carbon atoms here. So move that like so. And that's going to go ahead and put a positive formal charge then right here, based on the way that we've drawn those electrons. There's certainly more than one possible way here to do this, by the way. You can certainly start moving the electrons around in multiple possible ways. The key is that at the end of this, you should end up with the same 4 resonance structures as I'm ending up with. If you don't, something has gone wrong along the way, but there's many possible correct orders to list these in. So just because you don't have them in the same order as I doesn't mean they're not right. All right, so the pi electrons here moving toward that positive formal charge to give us our third possible resonance structure. We'll go ahead and draw that in. Boom, boom. Positive formal charge is now on this carbon atom. And then we'll go ahead and draw in the fourth and final resonance structure, I believe, here. So our fourth and final resonance structure, we're going to move these pi electrons over to here to give us our fourth resonance structure. Like so. And our positive formal charge is right there now. So that will be our 4 resonance structures to illustrate how the molecule is stabilized. The dominant resonance structure, the one that's going to contribute most to the actual hybrid structure of the molecule, would be this guy right here, because it has maintained the aromaticity, and we talked when we were going through Huckel's rules and defining aromaticity about why the aromatic ring is a particularly stable system itself. So this is going to be the most favorable resonance structure. And this is what's going to correspond to the major final product that we would observe here. So the structures that we're seeing as those three resonance structures toward the right are the minor contributing structures, but they are certainly doing their job of stabilizing that positive formal charge by delocalizing the electrons. It's just the one on the left here is going to be the dominant form, and so that's what's going to lead to the major organic product that we would observe. And generally when we're thinking about reactions, we're here thinking about what the major organic product is going to be, so it's going to correspond to the major intermediate, the one that's contributing most toward the actual hybrid resonance structure. So we're going to carry through with that orange boxed in structure here to go on to the next step of the mechanism. So the next step of the mechanism is that we're going to have a nucleophilic attack at that benzilic carbocation. So second step of the mechanism, nucleophile, whatever that is, attacks the benzilic carbocation. So we've got our aromatic ring here, and now I'll go back to abbreviating the structure by drawing a circle inside of the six-membered ring. Got our positive formal charge here at that benzilic position. And now what we're going to do is bring in our nucleophile, so that's our CH3OH, and its lone pair electrons are going to come in, acting as a nucleophile to form a bond to that carbon atom to give us our next intermediate. Okay, so our CH3OH, we got the proton on there that we will need then to finally, as our last step here, deprotonate to get to our final product. So nucleophile is attack the benzilic carbocation, and then finally, last but not least here, step 3 of our mechanism is going to be deprotonation to give that final product. Take our aromatic ring. And we need a proton acceptor here. We look back at what's available in the reaction, and methanol is there as a source of lone pair electrons to accept that proton. So we'll have those electrons come over, grab the proton, break that oxygen-hydrogen bond, and lead us right into our final product here. So now we basically created a new ether molecule as a result of this. We'd also, at the end of this, have our protonated alcohol molecule, which could subsequently lose a proton there, transferring it onward for further reaction. So our final product here is going to be this ether where we've done nucleophilic substitution at the benzilic position. And this is particularly favorable because of the fact that that benzilic carbocation is so stabilized. As our next example, we're going to take a look at a reaction and try to propose a mechanism to explain the product that's observed here. So let's say that we were to go ahead and take this molecule and mix it with water. And what we observe in the flask at the end of the reaction, we could characterize, for instance, using NMR, is a molecule that has a benzilic hydroxy group. So we're going to ask the question of, what's a reasonable mechanism for this reaction? So we're saying that we start off with the molecule that we see here on the left, our chlorine substituted molecule. And notice that the chlorine there is not at the benzylic position. But then we get a product here where the hydroxy group is at the benzylic position. So we need to ask, in this nucleophilic substitution, what is going on in order to move the substituent during the course of this reaction? Why are we starting with the chlorine not at the benzylic position, ending up with a hydroxy group at the benzylic position? So we're going to take a look at the mechanism for this reaction as a way of trying to explain why we're making this observation. So looking through the mechanism here, first step of the mechanism, when we're thinking about nucleophilic substitution, we either have, for these substitution reactions, SN1 or SN2. Remember that SN2 corresponds to the nucleophile coming in and attacking at the same time the leaving group is leaving. You cannot see rearrangements as a result of SN2. So I'm thinking SN2 is out here because definitely our chlorine group is at a different location than the hydroxy group. So we are having some sort of rearrangement taking place here during the course of the reaction. So SN1 is the mechanism that we need to go with here. And so in the SN1 mechanism for nucleophilic substitution, the first thing that happens, as we saw up the page just a bit, is the leaving group leaves. So we're going to break away that chlorine group to give our intermediate. So when the chlorine breaks away, that's going to give us a carbocation intermediate. Right here, that's a secondary carbocation. And remember that when we've talked about carbocations in the past, one of the concepts we've discussed is carbocation rearrangements, where if we can move a hydrogen atom or a methyl group in order to generate a more stable carbocation, that's generally going to be a favorable thing to happen. So our second step here that we need to think about is carbocation rearrangement. Carbocation rearrangements are going to be a common way that we end up with a nucleophilic substitution where the leaving group departs from a different location than where we observe the nucleophile in the final product. And that's exactly the case that we're seeing up here. Our leaving group, the chlorine, is leaving from a different location than where we're observing the hydroxy group coming in. So that's something that's going to lead us down the road of thinking that there's probably a carbocation rearrangement going on here. So in our carbocation rearrangement, we always need to be rearranging to make a more stable intermediate out of a less stable intermediate. So we're starting off here with a non-benzylic carbocation, and we have to ask ourselves what we could do to make this more stable. So for carbocation rearrangements, we need to always be doing this to increase the stability of the carbocation during the process. And so we could do that, for example, by turning a secondary carbocation into a tertiary carbocation. And looking at our structure here, the only ways that we can do this are by a 1-2 shift, meaning moving a methyl group or a hydrogen from one carbon atom to the next. And I don't see any way here with our current carbocation that we could move a group, a methyl or a hydrogen, by one position to take that secondary carbocation and convert it into a tertiary carbocation. So another option that we have here is that we could create a Benzilic carbocation by a 1-2 shift. Because we saw that those Benzilic carbocations have particularly high stability. So we could create a Benzilic carbocation by a 1-2 shift, again, of a hydrogen, called a hydride since we're moving it with its electrons, or a methyl group. So we're going to create a Benzilic carbocation here by a 1-2 shift. I think that's the route we have to go because looking at option number 1 here, there's no opportunity for us to create a tertiary carbocation out of a secondary carbocation here. So instead, we're going to create a Benzilic carbocation by a 1-2 shift, and this is an excellent option because definitely we've seen that Benzilic position is a very highly stabilized position. So taking a look at what we have available here to move about, we have 2 hydrogen atoms here at the Benzilic position. And if we take one of those 2 hydrogens and move it over with its electrons, so we're doing a hydride shift here. Hydride is our hydrogen with the 2 electrons coming with it. So once we do that, what we're going to end up with as our structure here is our aromatic ring. And now we would have a CH2 group here, so no longer a formal charge, but at this position it would just be a CH group there at the benzylic carbon. And so now that CH group, since it only has 3 bonds to carbon, is going to have a positive formal charge. And so now we've got this benzylic carbocation. Which is going to be greater in stability as a secondary benzylic carbocation than our starting material was, which was just a secondary standard carbocation. It's not immediately adjacent to an aromatic ring. So now we've created a more stable intermediate, and this is looking really promising because now we have our carbocation there at the benzylic position, and we notice that our final product corresponds to bringing in a substituent at that benzylic position. So that seems to suggest to me that we're on the right road here with creating a reasonable mechanism. So on to step 3 of our mechanism. Step 3 of our mechanism, the nucleophile is going to attack the carbocation. So we take our aromatic ring, and we've got our benzylic carbocation here. Water comes in as our available nucleophile. So we bring our electrons over, that attacks that carbocation. And now we can go ahead and draw out our next intermediate, and we're going to be 1 step away here from that final observed product. So now we have our water directly bonded there, so OH2. We have a lone pair of electrons there and a positive formal charge. And then last step of the mechanism, after the nucleophile attacks the carbocation to give this new bond to the water molecule, we need to deprotonate that water in order to give us a final neutral molecule as our product. So the nucleophile attacks the carbocation, and finally deprotonation to give a final product that has no formal charges in it. So that's going to give us our final observed alcohol product here. So we've got our aromatic ring with our water molecule bonded to it. And we have our positive formal charge on there. And our source of a lone pair electron set to act as a base here is going to be another water molecule. So bring that over, grab our proton, break the proton oxygen bond there, and that's going to lead us right into our final product here. So our final product is going to have that hydroxy group there at the benzylic position. We'd also get H3O plus out of this reaction mechanism step, and this, our final product here, corresponds to having that alcohol group at the benzylic position, so we are good to go here on this nucleophilic substitution. I should note here that we can also have SN2 reactions taking place at the benzylic position if we have a primary benzylic halide, for instance. Primary benzylic halides are going to tend to react in SN2, particularly if we have an anionic nucleophile. So you have an anionic nucleophile that's going to tend to favor an SN2 reaction. So for example, if we're talking about SN2 reactions, it's typically going to involve a primary benzylic carbon, specifically one with a leaving group, so CX, our halogen. And it's also typically going to involve an anionic nucleophile. So things like cyanide ion, that being Cn minus with a negatively formal charged carbon, azide N3 minus, etc., all of the different anions that were talked about in chapter 9 as anionic nucleophiles are applicable here. So as just one example, we could have sodium azide. The sodium azide is a very typical example of a anionic nucleophile. And remember that the N3 here is our abbreviated structure for one of the possible Lewis structures. There are multiple Lewis structures that could be drawn here, but it's basically 3 nitrogen atoms bonded together, where the middle one here with 4 covalent bonds is positively formal charged, the 2 on the ends are negatively formal charged, so that's a net charge of -1 there. And what's going to happen here is that in this SN2 mechanism, remember SN2 is a one-step reaction where the nucleophile comes in, that's going to be one of those terminal nitrogens, at the same time that the leaving group breaks away, which we can see here. So we'll go ahead and draw in the product of this SN2 reaction. Which would give us a product of CH2N3. We could also draw this out more explicitly if we wanted, which would correspond to having a single bond there to the nitrogen, and so on down the line here. And there are multiple resonance structures that we could draw for that N3 group there, but that's going to give you your new bond between the azide group and the carbon. And this is going to be a SN2 reaction because it's going on at a primary carbon at the Benzilic position, and we are using an anionic nucleophile. So these are the factors that are going to favor doing an SN2 reaction instead of an SN1 reaction, because it's going to be most favorable here for the nucleophile that's anionic to come in at the same time the leaving group is breaking away, and that's if you have a primary carbon. This is going to be a more favorable thing than creation of the carbocation, because this is going to be the faster process to take place, is for the nucleophile to come in at the same time the leaving group leaves. That's going to be faster than the process of breaking away the leaving group first to create a carbocation, which would be an SN1 mechanism instead. So SN2, if we have a benzylic carbon bonded to a leaving group and an anionic nucleophile attacking it. So now let's talk about some other reactions at the benzylic position that go beyond these SN1 and SN2 type reactions. So another type of reaction that occurs at the benzylic position is free radical halogenation. So free radical halogenation, we can think of analogously to back in chapter 8, you talked about free radical halogenation at the allylic position, and you talked about free radical halogenation of alkanes. Similar concept here, in that at that benzylic position we can form very stable radicals through resonance. And I'm not going to write out all the resonance structures here for the benzylic carbon radicals. You should be able to do that on your own. Keep in mind that the structures there are going to be very similar to the structures with the carbocation benzylic resonance, except that we'd have unpaired electron instead of a positive formal charge, but similar route there in that we're going to be delocalizing that unpaired electron across several carbon atoms of the aromatic ring. So we're going to see the benzylic carbon radical is stabilized by resonance, and that's going to make its formation particularly favorable. So we're going to see that halogenation at the benzylic position is a particularly common thing to occur. And so if we took a look at thinking back to chapter 8, what we saw was that if we took a alkane, such as we'll just do butane here as an example, and we reacted that with chlorine, we'll say Cl2, in the presence of light and heat, The light and heat there is absolutely essential because that's what's going to be used to generate radicals. Radicals are going to require the energy from the light or heat here in order to be generated. So that's one clue to you that a radical reaction is taking place, if you see that light and heat being present there. And what's going to happen here, we'll go ahead and say that we're assuming monosubstitution, because it is possible for these reactions to continue onward to give multiple substitution. But we're going to assume that it's monosubstitution for our purposes, which means that we're going to be replacing one of the hydrogen atoms with a chlorine. We're going to replace the most substituted carbons, hydrogen, with a chlorine, because that would correspond to the intermediate that would be the most stable, the most alkyl substituted carbon. So rather than replacing the hydrogen on one of those methyl groups with the chlorine, we're going to be replacing one of those secondary carbons, hydrogens, with a chlorine atom. So we're going to do that here within the middle of the molecule. So I'm just going to convert one of those CH2 groups to a CHCl group, like so, because this is going to be a secondary carbon, so we give a secondary carbon radical rather than right here, which would be a primary carbon, and would therefore give a primary carbon radical. So our secondary carbon radical would correspond to the most stable intermediate that we could make here, and so that's going to lead to the major product. So that's what we get when we think back to chapter 8. We can do reactions very analogously here at the benzylic position, because similarly, we would be able to form radicals at the benzylic position relatively favorably because of the resonance stabilization, the delocalization of electrons at that position. So looking at our benzylic position, carbon radicals, we'll go ahead here and take a look at propylbenzene. We're going to react that with Br2. A common solvent for this is carbon tetrachloride, CCl4, so I'm going to throw that in here mostly to distract you, but be aware that CCl4 is a common solvent. It's not going to react with anything that's present here, and we're going to throw in our light and heat. And what's going to happen here is that the carbon radical that we had formed, if we went through the full mechanism for this, we would be generating a carbon radical at that benzylic position. This would be our carbon intermediate, carbon radical intermediate, stabilized by resonance. And I'm not going to draw out all the different resonance structures for you. It goes back to drawing those carbocation resonance structures is analogous to what you would be doing here. And you should be able to do that. And based on that intermediate, the final product that we're going to get is going to correspond to plugging on the bromine atom right there at that benzylic position. So the benzylic position substitutions are favorable because of the fact that the benzylic radical position is so stabilized. So that's where you're going to go for if you are doing free radical halogenation. Aim for the benzylic position because that's going to have the most stable intermediate and therefore is going to lead to the most favorable product. As a reminder, sometimes you will see free radical halogenation reactions where we have N-bromosuccinimide as the reactant, NBS for short. So we're going to start with toluene here. And I'm going to put over the reaction here NBS, which is commonly used with peroxides as a source of initiation of radical formation. So the peroxides can be used in place of some of that light that's typically used. I'm going to throw CCl4 in here. Remember that that's just a solvent, and I'm going to also say there's light present here. So NBS, N-bromosuccinimide, what you need to be aware of about that is that N-bromosuccinimide is going to be our source of bromine radical for the reaction. So N-bromo stands for a nitrogen that has a bromine bonded to it. Succinimide is the parent structure of this. And the chemical structure for N-bromo-6-cinnamide has that bromine nitrogen bond. That's what's going to break to give the bromine radical for the reaction so that we can get substitution using the bromine radical. And we have our two carbonyl groups here. So our imide group is the nitrogen with those two carbonyl groups bonded to it. And we've got our N-bromo group there, our nitrogen bonded to our bromine atom. And so this is going to donate a bromine to the reaction. And it's going to be a radical-based reaction. That bromine is going to become bonded to the molecule at the benzylic position, because the benzylic position is where we can form our most stable reaction intermediate. So I'm just going to go ahead and take that one carbon chain, bond it to bromine, and we are good to go here on this. Also, as a result of that reaction, if you're wondering what happened to N-bromo-6-cinnamide, basically it's going to gain the hydrogen atom that was lost from the benzylic position. So the benzylic position started off as CH3, it became CH2, and that hydrogen that was lost there is what becomes bonded to our N-bromo-6-cinnamide. So the N-bromo-6-cinnamide at the end of the reaction has lost its bromine group there. So that's going to be our free radical halogenation reaction, the second type of reaction that we can talk about at the benzylic position, in addition to what we talked about earlier, which was the nucleophilic substitution reactions. The third type of reaction that we're going to talk about occurring at the benzylic position is going to be oxidation. So we talked about oxidation back in the last part of Organic 1, in Chapter 10. Oxidation was discussed, which is generally we're thinking in terms of oxidation of oxygen atoms. We're referring to an increase in the number of bonds between carbon and oxygen within the molecule. So we're going to look at oxidation at the benzylic carbon. The benzylic carbon is really susceptible to oxidation because of the fact that it forms relatively stable intermediates, as we saw in the cases of the above radical reactions. So oxidation of the benzylic carbon, what's going to happen here is that if we take any organic molecule, so I'm just going to start with ethyl benzene, and I'm just going to put O in brackets here to denote oxidation, because there's going to be many different oxidizing agents that we can use here, and so for now I'm just keeping it general. What's going to happen if you treat a molecule that has a benzylic carbon with an oxidizing agent is that you're going to end up converting that benzylic carbon into a COOH group. So you're going to convert it into a benzoic acid. Benzoic acid, by the way, is a really common food preservative. Sometimes it's converted into the salt form by deprotonating it to form benzoate. So if you see things like sodium benzoate, that's a really common food preservative that's often listed toward the tail end of the list of ingredients of different food items. So benzoic acid is what the product would be here, and the oxidation process corresponds to oxidation at the benzylic position. So the benzylic position gets oxidized to COOH. So we're converting basically alkane carbon here, we could think of it as, to a carboxylic acid. And you may be wondering, we've got an extra carbon in the chain here that we haven't accounted for. That seems to have just disappeared. So if we're counting carbons here, we've got our first carbon off the chain, which corresponds to this carbon of the benzoic acid, carboxylic acid group. The CH3 would become CO2 during this oxidation process. It gets oxidized as well. And we're not going to go ahead and write that. The CO2 is gas. It's going to float away. It's not going to be something that you would be collecting in your reaction flask. So the compound of interest here is just going to be the molecule that corresponds to replacing the benzylic carbon with COOH. And so let's talk about some specific oxidizing agents here that we can use to carry out these types of reactions. And many of these oxidizing agents should look familiar from Chapter 10. Several in this list are going to be the same oxidizing agents that we would use to oxidize alcohols. So these are what we could use to fill in that O there. So oxidizing agents are going to be things like chromium-based reagents where we have chromium-6. So examples of chromium-6 are going to be CrO3, H2Cr2O4, chromic acid as it's also called. We could also do a mixture of H2SO4, NaCr2O7, and water. That would give us, as a result of that, chromium in the chromium-6 oxidation state, suitable for oxidizing. We can also use potassium permanganate, KMnO4, as an oxidizing agent there, totally suitable, and that has manganese as manganese 7 there if you're taking track of what's going on there. There are also enzymes that will interestingly carry out oxidation reactions. Those enzymes are often referred to as cytochrome P450s. So enzymes in the human body and other organisms will catalyze oxidation reactions, and those are called cytochrome P450s. They're usually specialized toward just a small subset of types of aromatic molecules, for instance, or other types of molecules to carry out oxidizing them. So they are very specific in the types of reactions that they carry out, because you wouldn't necessarily want for a cell to have a non-specific enzyme that is oxidizing everything. You generally want it to be done in a targeted way. And so cytochrome P450s are specialized enzymes to carry out that function. So let's take a look at a couple of examples of this oxidation. Hopefully this isn't too bad. We're not going to go through the mechanism for this because it's a relatively involved mechanism, but we can look at a couple of examples to highlight what's going to happen in some different scenarios with these types of oxidation reactions. So we're going to take a look at this organic molecule. We can react with potassium permanganate, KMnO4, and what's going to happen here is that each of the benzylic carbons is going to be oxidized to give a carboxylic acid group. So we get COOH here, and then para to that, also COOH at that para position as well. So get full oxidation going on there at each of the benzylic carbons. There is one important caveat to this, and that one important caveat is that the benzylic position has to have a carbon-hydrogen bond available. So we'll go ahead and write that down, that the benzylic position must have at least one hydrogen bonded to it in order to be oxidized. If there's no hydrogen directly bonded to that carbon at the benzylic position, meaning if there's no benzylic hydrogens, there can be no oxidation at that position. Because what's happening during the oxidation process is that the carbon-hydrogen bond is breaking in order to create a carbon-oxygen bond of the carboxylic acid. So let's take a look at this example problem here. So let's say we subjected this to an oxidizing agent, for example. CrO3. And looking at what we have available here, our methyl group over here can definitely be oxidized, so I'm going to convert that to our carboxylic acid group, our COOH group. On the other hand, though, this carbon has no carbon-hydrogen bonds directly there at the benzylic position. Our benzylic position is this carbon that I put a dot on, and that would be described as a quaternary carbon. And so at that quaternary carbon, we have no reaction that can take place. So I'm just going to draw that in exactly like it was to start with, because there will be no reaction there at the benzylic position. So remember that in order for oxidation to take place, you absolutely have to have a carbon-hydrogen bond at the benzylic position. Otherwise, there can be no reaction taking place there. So that about concludes things for reactions of aromatic rings, and that does it. Be sure and take a look at reading for chapter 21. The reading for chapter 21 is 21.1 through 21.3 and 21.5. That was written up on the board last class period where we had this discussion. So next class period, what we'll be doing is moving on to chapter 22. We're going to be looking at reactions of the aromatic ring that will give these different substituents. So we're going to be asking the question, how in the world would we start with benzene and add a methyl group to the ring? How would we start with benzene and add a tert butyl group, such as what we're seeing up here in the reaction that's on the screen? So we're going to ask the question of how we go about taking benzene rings and functionalizing them next time we meet up. So that is about it for today.